Okay, I have been very, very loose with my language and with my charts. I've been saying the antiderivative. Antiderivative, I don't necessarily have the word the in there, but antiderivative. I've been saying the antiderivative. That was wrong. You can forgive me or not, doesn't matter. We're going to correct it right now. So back to the x squared. And I want an antiderivative. Now notice this time I said an antiderivative. I want an antiderivative of x squared. And so what I told you was 1/2 x. That's wrong. That's not what I told you, because that wouldn't be the antiderivative or an antiderivative. What we learned a couple pages ago, I said, oh, 1/3 x cubed. And I said, oh, that works, because that checks. And that's all we said. But I could have just as easily said this. I could have said 1/3 x cubed plus, 96. Nothing special about the 96 at all. It's just the number that came in my head. Because notice, that checks too. But that's going to equal 1/3 times 3x squared plus 0 for x squared. And I could do this again, and I could say 1/3 x cubed minus 122.8. And again, nothing special about the 122.8. It's just what came in my head. But notice that checks too. When I check by differentiation, that constant on the end, its derivative is 0, and so I get back to x squared. And I literally could do this forever, except I would die at some point. But you could continue to change that number on the end to any constant you wanted, add, subtract, whatever constant you want. And that's what I've got down here. The point is that x squared has infinitely many antiderivatives. In fact, all functions have infinitely many antiderivatives. For any given function, its antiderivatives will be the same except for a constant added or subtracted on the end. To allow for the fact that one function has many antiderivatives that differ only by a constant, we define the most general antiderivative, which is this. If capital F of x is an antiderivative of little f on an interval I, then the most general antiderivative of little f on I is capital F of x plus c, where c is an arbitrary constant. And so what I should have been doing on each and every one of these things here is I should have written 2x plus c, mx plus c. 1/2 x squared plus c, 1/3 x cubed plus c, 1/4 x to the fourth plus c, all the way down the line, plus c, plus c, plus c, plus c. You get the point. I should have been adding plus c's on all of them. And that plus c is just our way of acknowledging that a given function has infinitely many antiderivatives that differ by a constant. So that plus c represents any sort of constant you might have there. Now, am I going to take off for a missing plus c? No. Although some teachers do. The computer, however, will take off for the plus c. And that's not something I'm willing to adjust your score for. You've got to remember that the computer wants that plus c there. And if you don't put the plus c, it's going to count it wrong. So just learn to put the plus c there. So now coming up with some more facts. Fact, the constant multiple rule. If capital F of x is an antiderivative of little f of x, then k f of x is the antiderivative of k capital F of x is the antiderivative of k little f of x. In other words, numerical coefficients can be factored out. And actually you are factoring it out, but we'll just go with parenthetically factored out. Makes sense. In differentiation, you could factor out a coefficient. That coefficients just kind of stayed there. They were part of the answer, but you didn't have to worry about them. That it was easy in differentiation. You could just write it down and not worry about it. Same thing in anti-differentiation. If you have a multiplied numeric coefficient, it can be factored out. You just write it down, do the rest of the problem. The sum difference rule. If capital F of x and capital G of x are antiderivatives of little f of x and little g of x, respectively, then capital F of x plus capital G of x and capital F of x minus capital G of x are antiderivatives of little f of x plus little g of x and little f of x minus little g of x, respectively. In other words, when finding antiderivatives, you may split up a function by adding and subtracting and work term by term, just like you can in differentiation. When you differentiated a polynomial, remember polynomials is the sum and difference of terms. When you differentiated a polynomial, you just worked term by term. You didn't care that there was a plus or minus sign between them. You just wrote down the plus or minus sign. Same thing in anti-differentiation. If it's just the sum or difference of terms you know how to do, well then you just do each term and work term by term. But here is the big thing. Note, it is not true for multiplication and division, just like it wasn't true in differentiation. In differentiation, when you had a product or quotient, multiplication or division, you either simplified it first or used the product rule or quotient rule. It was special and sometimes hard in differentiation, therefore it's going to be special and harder in anti-differentiation. It's going to turn out that anti-differentiation is much harder than differentiation because you're doing something backwards. Anytime you do something backwards, it's harder. So if it was special and hard in differentiation, like products and quotients and compositions, it's going to be special and harder in anti-differentiation. So for anti-differentiation and differentiation, you cannot break up products and quotients. You can't. You just can't do it. Either you simplify them first, and in the case of anti-differentiation, if you can't simplify, then we're going to have a whole host of things that might work. Okay, let's do some problems. Find the most general antiderivative of each of the following. Now you're going to do some basic same stuff that you did with differentiation, which means if you can simplify the original function, you're going to simplify the original function. So that's what I'm going to do here. I'm going to say that's x cubed minus 2x plus 3x to the 1/2 plus 2/3 x to the negative 4/5 plus 7. We like exponents, so rewrite it with an exponent. And this guy right here, remember we don't care too much about coefficients, so I just wrote the 2 and the 3 as a coefficient. Then since the x was in the denominator, I brought it to the numerator with a negative exponent. The 5, the index, is my denominator. The 4, my power, is my numerator. But that's still the original function. And so now my antiderivative. Just working term by term. Increase the exponent by 1, multiply by the reciprocal, the new exponent. This is understood to be 2x to the first. The minus 2 is just a coefficient, just write it down. Increase the exponent by 1, multiply by the reciprocal, the new exponent. The 3 is just a coefficient, just write it down. Increase the exponent by 1, 3/2. So that was 1/2 plus 1. Multiply by the reciprocal, the new exponent. 2/3 is a coefficient, just write it down. Increase the exponent by 1. Multiply by the reciprocal, the new exponent. And then finally, the antiderivative of a constant. Be sure you remember you're doing an antiderivative here. So you're asking yourself, what has a derivative of 7? That'd be 7x. And then we put on that plus c. And so all of these guys basically were increase the exponent by 1, multiply by reciprocal, new exponent, and then make it look a little prettier. And so that's 1/4 x to the 4th minus x squared plus 2. Okay, that x to the 3/2. At this point, I don't care how you write it. You may leave it x to the 3/2, or if you want to call it the square root of x cubed, I don't care. If the computer cares, give the computer what it wants. But for me, I just want basic simplification, so the 3's are going to cancel. You can leave that as x to the 3/2, or if you want, you can call that as the square root of x cubed. I don't care. I don't care at all. That's going to be 10/3, and I'll just go back to the 5th root, but I don't care. Leave it x to the 1/5 if you want, or go back to the 5th root, plus 7x plus c. And then if I had space, I would check this to confirm that that is the right answer. You can check by differentiation. Now, a lot of these you can check by pretty much just looking at it. The derivative of 1/4 x to the 4th would be x cubed. The derivative of x squared would be 2x. Here that's x to the 2/3. When I multiply by, or that's x to the 3/2. If I multiply by the 3/2, the 2 would cancel, leaving me 3. And then then decrease the exponent by 1 would give me x. That a lot of these you can check by just looking at them. You just differentiate your answer. It has to go back to the original problem. Okay, next guy. That's scary looking, but we can do it. Again, it says adding or subtracting. So the antiderivative. Term by term. That 3 just hangs out. Then we've discussed repeatedly the effect of that 2. If I were differentiating, the effect of that 2 would be to multiply it. This is anti-differentiation, so I'm going to divide. Then I ask myself, what has a derivative of cosine? And that is sine. Angles do not change. The 4 just hangs out. Then I ask myself, what has a derivative of secant tangent? And that'd be secant. Okay, this guy right here. So that'd be cosecant squared pi over 12 times x. So that pi over 12 is just a coefficient, just like this 2 was. The rule when I anti-differentiate is I divide by that. Well, dividing by pi over 12 is the same thing as multiplying by 12 over pi. Then I ask myself, what has a derivative of positive cosecant squared? Well, because I want it to turn out to be positive, I'm going to need a negative there. So the derivative, what has a derivative of cosecant squared is cotangent, but I got to take care of the negative because the derivative of cotangent is negative and I want to end up with a positive. So I need another negative there. Angles do not change. I'm going to drop down because I'm running out of room. What has a derivative of e to the x? Well, e to the x is its own derivative, so it's its own antiderivative. And then lastly, the effect of that 3 is to divide by it, and then e just repeats itself. So 1/3 e to the 3x plus c, and that's a good place to end this video.